Let's say we had a function f of x equals x squared, which we can graph on a grid, and it looks something like this. And we were interested in finding the area under the curve. And the area we want to find is over the interval 0 to 1. One way to do this is to break our interval into a series of subintervals. Let's say we'll break it up into 4 equal subintervals. So if we came here and this was a quarter and a half and 3/4, we'd have 4 subintervals over the interval 0 to 1. Then let's draw a vertical line from the right-hand part of our interval up to the curve and make a point which would represent the right-hand endpoint. Then let's form a rectangle with our adjacent interval like so. And then repeat the process for all the other right-hand endpoints of our subintervals. So for 3/4, the right-hand endpoint would be here. Form a rectangle with the adjacent subinterval. For a half, the right-hand endpoint would be there, forming a rectangle with the adjacent subinterval. And finally, for a quarter, it would be here, forming a rectangle with our adjacent subinterval. Then, if we calculate the area of all these 4 rectangles that we've created, this will give us an approximation of the area under the curve. Let's call the area of the first rectangle A1, the second rectangle A2, third rectangle A3, and the fourth A4, such that area total is equal to A1 plus A2 plus A3 plus A4. Now let's figure out the values of the right-hand endpoints. Well, we know that this point here, x is going to be 1. So if we substitute 1 into our function, x squared, we'd end up with 1 squared, which would be 1 as well. So the right-hand endpoint for the fourth rectangle is 1, 1. Similarly, the right-hand endpoint for rectangle 3 would be 3/4 for x. Substituting that into the function, we'd end up with 9/16. And so on. So the right-hand endpoint for the second rectangle would be 1/2 for x. Substitution into the function would give us 1/4. And for the first triangle, x would be 1/4, and y, or f of x, would be 1/16. Okay, now we can go ahead and figure out the areas of each of the 4 rectangles. So the area for the first rectangle would be length times width, or height times width if you prefer, which would be this distance here, which is the height, and this distance here, which is the length. So we would end up with the height being 1/16 and the width being 1/4. And for rectangle 2, the length would be this distance and the width would be this distance. So our area for rectangle 2 would be 1/4 times 1/4. And for rectangle 3, our area would be this distance here times this distance here, which would be 9/16 times 1/4. And finally, for rectangle 4, the area would be this distance here times this distance here, which would be 1 times 1/4. Okay, I've rewritten the equation here, cleaned it up a little bit because it's getting rather busy. To finish off, we can work out each of these parts of our equation. So the first area would be 1/64th plus 1/16th for the second. Third would be 9/64ths. And the fourth would be 1/4. And to add these fractions, we would need a common denominator, which would be 64. So 1/16th would be represented at a 64. 16 times 4 is 64. So the 1 times 4 would give us 4/64ths for the equivalency of that fraction. Similarly, for the 1/4, we'd have to multiply by 16 to get 64ths, which would give us 16/64ths for that fraction. And continuing to solve it, we'd get 1 plus 4 is 5, plus 9 is 14, plus 16 is 30/64ths, which is also in decimal form equal to decimal 46875. And we could add in whatever units squared that we're going to be using. So in the end, we find out that using the right-hand endpoints, our approximation for the area under the curve is 0.46875 units squared. And we will know by looking at the graph that this approximation is greater than the actual area under the curve. And if we wanted to get a better approximation of the area under the curve, we would increase the number of subintervals so that the width would be smaller. Eventually, what we're looking for is getting that width limit approaching 0 to get a much, much better approximation of the area under the curve.